Good morning, students. Today we are going to start off with the second lecture on characterization technique. We are going to continue with the introduction part because there are some more things that we should know before we can actually start off with any specific topic like X-ray diffraction or UV visible spectroscopy and so on. So last class we have seen a number of techniques being listed down. Some of the techniques which I said was optical, and then AFM, then SAM, TEM, and so on. But what kind of technique you use actually also comes at a cost of both finance as well as time. So if you want to do any kind of experiment which is dealing with optics, any kind of characterization which deals with optics, the time and the cost both are at the lower end. So here we have this part where time and cost is not much, but as we keep on going to higher and higher order of characterization or different kinds of characterization, for example, let's say AFM, the atomic force microscopy, the time needed is a bit more and the cost is also a bit high. But then when we go from optics to something like electron microscopy, the source changes from visible light to what we call as electron. So when we go into something like a scanning electron microscopy, the cost as well as the time is high, right? And then we go for tunneling electron microscopy, the cost and time is even higher. So in tunneling electron microscopy also we have some other techniques like high resolution tunneling electron microscopy. The time and cost even would be higher. This is a very rough schematic to give you an idea that all experimental methods which takes more time and more cost comes at a greater price for sure. Okay, we need to compromise a lot of factors depending on what are our requirements here. So this table you might have seen before, because I think we have discussed it in our initial classes also when we are talking about electromagnetic radiation. So the frequency range and wavelength has already been given in your classes. But if we just look into the transition that we are talking about here for let's say gamma ray. Now the gamma rays are basically happening because of a nuclear transition. The X-rays, I think we already know these are because of the inner electrons, because you might have studied how X-rays are produced. Now, we will also give a brief of that when we start in our next lecture, how X-rays are produced. But in general, when we talk about X-rays, there were some characteristic X-rays which are also produced depending on the transition of the inner electrons from one energy level to another energy level. For ultraviolet, we are actually talking about the transitions of outer electrons, same as visible light, which is also because of the transition of outer electrons. This transition process and why these radiations are emitted, I think it's clear to you, might have come across this a number of times, but we are going to discuss it briefly in our next slide. Near infrared region, we need to remember that it's because of outer electron, but at the same time it is also because of the molecular vibration. Now please remember, this near infrared region is very close to visible light. So if there is a transition from visible light to infrared, if there are some outer electron transitions, it's possible that it's a combination of visible light and near infrared radiation. But as we go into the other part of infrared, like far infrared and mid infrared region, we have the molecular vibration that actually takes place, because of which we are getting the infrared radiation. And then we have got the microwave. So microwave is because of molecular rotations, and also because of the electron spin flips. So these are the types of transition from this slide. Definitely you need to know what is the frequency range and what is the wavelength range. Both are interdisciplinary. I hope we remember this, because we have done these things, because we have come across a number of times E is equal to h nu, which is equal to hc by lambda. These things should come to you very naturally. Okay. So we can see that the frequency is actually inversely proportional to the wavelength. So it is inversely proportional to the wavelength. So obviously if the frequency here keeps, you can see this as we go from gamma ray to microwave, the frequency will keep on decreasing, right? So if the frequency keeps on decreasing, the wavelength will keep on increasing. So you have to remember this sequence. That's very important. And also from your examination point of view, test point of view, quizzes point of view, you need to know what are the types of transition that actually happens, because of which you've got gamma ray, X-ray, and so on. So let's go to this. What happens when light interacts with a molecule? I think this is in the first lecture, the initial video that I have given you, where you have listened to this. So interaction of light with matter is or molecule is very important. Now this interaction of light might be with the atom, or with the molecule, or with the solid, or the absorber, as we say. So whenever there is an absorption, I hope all of you remember this, because I think we have discussed this before in our class also. So in case we have lower energy level, let's say E1, and the upper energy level, let's say E2, and we have got E1 is less than E2, okay, and we have, let's say, an atom here. It might be an atom, it might be an electron, it might be a molecule, and so on. Okay, so we don't need to think about this. There is only, we're talking about the transition of from a lower energy level to a upper energy level, right? So when there is an interaction, let's say we have got some kind of radiation falling on it. So we have got some kind of radiation falling on it. This particular atom, which is at the lower energy level, will actually jump up, and it will go there. What happens to this radiation? This radiation basically gets absorbed, right? So this radiation actually will get absorbed. So this gets absorbed. So this radiation is absorbed, and we have got a transition from the lower energy level to the upper energy level, and that is what is absorption is all about. So we don't have any output, so there is nothing which is coming out, right? Nothing which is coming out. So next, if we go, we can go to something which we call as the emission. Now if we go into the previous picture, we have this. So we have got the energy levels. Now this atom is already on the upper energy level. Now it cannot remain there forever. It basically needs to come down. So what will happen is, it will basically come down, okay, after some time. And as it comes down, since we have got energy E2 is greater than E1, when it comes down, in order to keep this conservation of energy, this will radiate some output, and that basically is nothing but the output energy, which can be written in the form of h nu. So that is what is emission is all about. But you please remember that it's not always mandatory that there should be some kind of radiation which is coming out. Sometimes it does happen that there is no radiation which is emitted when the transition is happening from upper energy level to the lower energy level, and this is called the non-radioactive decay. So please remember this term of non-radioactive decay, because that's important. So non-radioactive decay, okay, so that's important. So we will go to the next part, what happens when light interacts with matter, and that is what is called the scattering. Okay, so if we have a scattering here, and we are talking about scattering, what happens in scattering and diffraction. So I think you have come across this term diffraction, okay, and you have come across the term scattering, right? So in diffraction, what happens is there is some kind of direction involved. If you remember your Young's double slit experiment, and if there is a, let's say, let's consider a single slit, we have got some wave fronts which are incident, and then the diffraction will happen, and it will be confined to its certain angle, right? But when we're talking about scattering, you might have some kind of molecule or dust particle, let's say, and the light gets scattered. So light may fall on this, and it gets scattered in different direction, okay, gets scattered in different direction. Some of the light might just pass through because it did not interact. This is something which is similar to Rutherford's scattering experiment. So when we are talking about scattering, the light will basically fall on the matter. So basically there will be an interaction, it will fall on the matter, but after it falls on the matter, it will be scattered, okay. And this light that falls or gets scattered may or may not incur a transfer of energy. That means the light might not transfer from a lower energy level, or might not transfer any kind of energy to the atoms or the molecules, which will allow the transition states, like the transfer of the atom from the lower energy level or to the upper energy level, or there, or the other way, right? So this is basically what is called scattering. It necessarily doesn't say that there will be some kind of transfer of energy. We might have the input, and the output will also be the same, okay, the same radiation will come out might be the wavelength will remain the same. So now let's talk about classification of methods. Now the type of spectroscopy basically depends on what kind of physical quantity that we are measuring. Okay, so what kind of physical quantity that we are measuring. So what we measure is basically the output. Now the output might be in the form of intensity, the form of energy absorbed or produced. So when you are allowing some kind of radiation to fall, let's say visible light is falling on on a material which allows partial light to flow through it, then you call that material as translucent. Okay, if it doesn't allow any light, that means it is opaque. So we look into the output. If it allows partial light, that means it's basically a translucent material. If it allows almost maximum light to pass through it like glass, then it's basically a transparent material. So depending on that classification or intensity of the light that is passed through, we can identify what kind of material we are talking about. So we can identify the property of the material, right? Okay. So if you talk about electromagnetic spectroscopy, it basically involves the interaction of matter with electromagnetic radiation. So basically, if you're talking about interaction of UV visible light, IR light, and so on, we are talking about electromagnetic spectroscopy, even infrared spectroscopy, and so on. So we're going to look into this in more detail later. When we talk about electron spectroscopy, it involves the interaction of electron beams. So the electrons will interact with matter, and that is basically electron spectroscopy. Auger spectroscopy, I think all of you have heard about Auger effect. We might discuss it later. So what happens, Auger effect, we are having an electron, and that electron if used for studying the material, that is nothing but Auger spectroscopy. Then we have got something which we call as the mass spectrometer. In mass spectrometer involves the interaction of charged species with the magnetic or the electric field, giving rise to a mass spectrum. Now you need to understand here that the charged species should be there. So if we have got a charged material, in acoustic spectroscopy, as the name suggests, we actually use sound, and we are going to use the frequency of sound as an input, and we are going to see what is the variation in the output of that frequency. When we talk about dielectric spectroscopy, it involves the frequency of an external electric field. So what do you mean by that? It means that you can use an AC signal here. We all know that DC signal, for DC signal omega, which is basically the frequency, is nothing but 0. Now that's 0 for DC, right? So we cannot use that. So if you want to use a frequency variation, we can actually use a AC signal here. So we can use an AC signal and vary the frequency to actually do the dielectric spectroscopic study. Next we have got the mechanical spectroscopy. Now this term is not often used, but it involves the frequency of an external mechanical stress. So we all understand what is meant by frequency. So we are actually using external mechanical stress, let's say a torsion which is applied to a piece of material. So we can twist it and basically twist it in a given interval of time for a given number of time, and then basically do the study, and that is what is mechanical spectroscopy is all about. So what are the materials and techniques? So everything, whatever we are actually using around us is made up of some kind of material, right? Or basically a combination of material. And these materials, it might be a metal, it might be a ceramic, it might be a polymer, it might be a semiconductor, or it might be a composite of all of them, or just two of them, or certain particular components. Okay, so we see these kind of materials in our daily lives, and what we are interested in characterizing these materials. Okay, so it is known, very well known, that the properties of all these materials are determined by the material's structure. So we have already studied a bit of solid state physics, and we know that what is the difference between a crystalline material and an amorphous material. So depends on what kind of material we want to study, and depending on that we are going to select the characterization technique. So if you consider the material structure to be, let's say, crystalline in nature, one of the most common characterization technique that comes in mind is XRD, okay, because it's going to talk about the planes and all the Miller indices and everything else. Okay, so we are going to use a characterization technique depending on what kind of material we are going to study. So therefore, to understand the material structure at all possible or relevant lengths, we apply all the basic principles of physics, chemistry and biology. So it's not that since we are studying physics, we are only going to talk about the techniques which has importance in the physics, but it's will also be interdisciplinary in nature, because nowadays if you are going for any kind of research, it's interdisciplinary. So we involve technique which has both physics, chemistry and biology involved. So if you want to do a study based on only physics, and you do an XRD, it doesn't mean that you cannot use in chemistry. Or if you do something like an NMR, you can definitely study the material and use it for improvement in the field of physics as well, right? So these basically plays a key role in deciding the resulting properties. So our aim is to basically have a material which is optimum in nature. Okay, so what we aim is we target a fabrication process and we try to optimize that fabrication process, and optimize in the sense that they can be used in different environments. Okay, and also at the same time, how do we optimize this? We characterize the material. So basically we might have some sample material and we will characterize the material, and we will see if it is fit for a particular use after characterization. If it is not, we are going to reprocess the system and we are going to change the processing system. We are going to change some parameters. So that plays a very vital role. So processing is something which determines the structure and it also determines the property. Okay, and performance depends on how much you can play with the cost, or how much reliable the product you need. Okay, so if it's very reliable, very cost effective, then the performance is definitely going to be very high. Okay, so it's very simple to understand. So basically, to design the scientific process of fabricating any kind of material, and to meet the needs of modern technology, we have to couple out a few things. First, what is the interacting process? Next, what is the mechanism involved? Okay, and of course, what is the material which can be determined using sophisticated instruments. Okay, with interdisciplinary approach. Okay, so what we do is basically we don't restrict ourselves to a particular subject. We want to find out a material which can be very efficient or very useful for a particular application. What we do is we use all kinds of possible technique to understand how optimum this material is, and then accordingly design our experiment. So the conclusion is to characterization of material has been one of the foundation pillars of material science. So if today we are talking about material science and we are saying its progress in the society, that's because we have got a lot of characterization technique, and we can use those characterization techniques in order to understand the material and how it behaves in different environment. Okay, so that's all for today. In the next lecture, we are going to talk about X-ray diffractometer. We are going to start with something basic. We are not going to extend the lecture too long, but this is basically how the instrument looks like in real. We already have it in our lab, and probably when the session starts, we can have a look at the instrument. These are the different parts of the instrument which we need to know. This entire thing is basically called the goniometer, and we are going to talk about these different parts of an X-ray diffractometer. Thank you.